Good morning. Today we have a third lecture, and our lectures will be devoted to the main part of the formal language and codes about words. This lecture is a continuation of the previous our lecture number 2. So we shall start. We call a word X from Формальні a capital star is called primitive if it is not a power of another word of this Формальні. Hence, we get that a word X is primitive if and only if the equality X is equal Y in power n with n from with n any positive integers implies that X is equal Y. Also, we remark that the empty word is not primitive. So, the first very interesting statement about primitive word is the following. Proposition 1.3.1. Each not-empty word is the power of a unique primitive word. We shall prove this proposition, and suppose X is a non-empty word, our alphabet A capital, and delta B is the restriction of the function gamma from free monoid our the alphabet A capital to into itself, and gamma is where gamma is defined by the formula gamma of empty word is empty word, and gamma from the word A V is equal VA for any letter A from the alphabet A capital and any word double V from this alphabet. And we put that delta is a restriction of this function gamma to the conjugate class of the word X. So we recall what is the conjugate word. If the word W has the property that it is equal UV, and all the word W prime is equal VU, then we shall call that W and W prime are conjugate words. So then we have that delta in power k is equal 1 for if and only if x is a power of the wall of the land which is dividing k. Let p be the order of the mapping delta, so that the great common divisor of the integer k, so that delta in power k is equal 1. Since delta in power p is equal 1, there exists a word r of the length p, so that x is equal r in power e, where e is some positive integer. The word r is primitive, otherwise there will be a word s of the length q dividing p, such that r belongs to the monoid generated by the word s, which in turn implies that x belongs to the monoid generated by the word s. This contradicts the definition of the positive integer p, yeah? That's it. This proves the existence of the primitive word. To show uniqueness of the primitive word, we consider a word T from a free monoid alphabet A capital, such that X belongs to the monoid generated by the word T, and we put K is the length of the word T. Since delta in the power k is equal 1, the integer k is multiply of p. Consequently, we get that t belongs to the monoid generated by the word r. Therefore, if t is a primitive, then we have t is equal r, and hence we proved the uniqueness of this presentation. So next, let X be a non-empty word over the alphabet A capital. The unique primitive word R such that X is equal R in the power n for some integer n is called the root of the word X. The integer n in this case is called the exponent of the word X. Proposition. Two non-empty conjugate words have the same exponent and their roots are conjugates. We shall prove this proposition. Let x and y be two conjugate non-empty words of alphabet A capital, and let I be a non-negative integer such that y is equal gamma in the power I of x, where gamma is the map is defined in the following: gamma of the empty word is empty word, yeah, and gamma of AV, where A is a letter from alphabet and V is any word of alphabet A capital is equal VA. So this map gamma permutate the first letter of the word on the end place of the new word. Yeah, it's this work in such way. Set R and S be roots of the word X and the word Y respectively, and let N be an exponent of the word X. Then we have that Y is equal gamma in power I of the word R in power N, and the definition of this map gamma implies that the y the following equality holds. Yeah, this shows that gamma in power r of r sorry, gamma in power I of the word I belongs to the monoid which is generated by the word S. Interchanging the role of the word X and the word Y, we have that similar or dual, including that gamma in the power J of the word S belong to the monoid generated by the word R. This follows that gamma in the power I of R is equal S, and gamma of the power J of S is equal R. Therefore, the words R and S are conjugate, and consequently, the word X and Y have the same exponent. This completes the proof of proposition 1.3.2. Next. The next proposition describes the conjugate class of same exponents. So what is a conjugate class? If we have some word, when we consider, so just a moment, if we have word W, yeah, we can consider any words W prime, so that from the Freemonoid our the alphabet a capital, so that W prime is conjugate word to respect to W, or in other sense, V and sorry, W and W prime are conjugate words our alphabet a capital. We consider with this class is denoted by C, yeah, and the following statement holds: all words in the conjugacy class have the same exponent. So, and if C is a conjugacy class of the word of the length n with exponent e, then the cardinality of this class is equal to n divided e. So it is obvious a relation to be conjugate is a relation of equivalence, and hence all words our alphabet A capital can be divided on class of congruence this relation, under this relation. So we shall prove this nice proposition. Let x be any non-empty word of the length n, and C be the conjugate class of x. Let delta be the restriction of the mapping gamma, which was defined a few minutes ago, and delta is the restriction of gamma onto the class C, and P be the order of this restriction map delta. The root of the word x is the word r of the length p, such that x is equal r in the power p. Therefore, we get that n is equal p multiply e. And now, when we consider our class C, it consists of the word x and other power of image of the word s under the map delta up to the power delta p minus 1, yeah, because the delta in the power p of x is equal s. This is an empty, this is identity map, yeah. All elements of this class are distinct because P is the order of the map delta, and therefore we get the cardinality of the class C is equal P. Next, we now compute the number of conjugated classes of the words of a given length our finite alphabet. Let A capital be an alphabet with call letters. For all positive integer n, the number of conjugate classes of primitive words in A capital star of the length n is denoted by ln of k. The notation is justified by the fact that this number depends only on k and not on A. The first value of this function for k is equal to 2, 3, 4 are given in the following table. So here for k equal 2, 3, 4, 5, and clearly that ln of 1 is equal 1 if n is equal 1, and ln of 1 is equal 0 in other cases. Oh, for positive integer n, we have that k in power n is the sum of such product d multiply ld of k, where d divides n, where d runs over the result of n. Indeed, every word of length n belongs to the exactly one conjugacy class of the word of the length n. Each class has d, which is equal n divides e elements, where e is the exponent of these of its words. Since there are as many classes whose words have exponent n divides e, as there are classes of primitive words of the length d, which is equal n divides e. The formula follows. We can obtain the expression for the numbers L n of k by using the classical technique of the Möbius inversion, which we now recall. The Möbius function is a function mu from the set of positive integer to the set of non-negative integer, defined by mu of 1 is equal 1 and mu of n is equal minus 1 is the power n if n is a product of I distinct prime numbers, and mu of n is equal 0 in other cases. Proposition. This proposition is called the Möbius inversion formula. Let let alpha and beta be two functions from the set of positive integers into the set of non-negative integers. Then a of alpha of n is equal to the sum of b of d, where d divides n for n less or equal 1 if and only if b is equal to the sum of the such product mu d multiply alpha of n divide alpha n divide d by d divides n for all positive integer n. We shall prove this formula. Let a set S be the set of function from the set of positive integer to the set of non-negative integer. Define a product on the set S by setting f star g of n is equal such sum, yeah, for any f and g from S. It easily verifies that S is a commutative monoid for this product. Its natural element is the function I capital taking value 1 for n is equal 1 and 0 elsewhere. So I propose you to prove that statement, two statements, as exercise. We have a first exercise for the practical work. Thank you. So next, let iota from S be constant function with value 1. Let us verify that iota star mu is equal I capital. Indeed, iota star mu of 1 is equal 1 if n is equal or great to, then we put n is equal p1 in power k1, p2 power k2, so on, pm power km. B is a prime decomposition of the integer n. If d divide n, then mu of d not equal 0 if and only if d is equal p1 in power ln, p2 in power p2, so on, pm in power lm, with all l1, l2, lm is equal 0 or 1. Then we get that mu of d is equal -1 in power 2 with 2, where 2 is equal the sum of li from I1 to m. It follows that iota star mu of n is equal such sum of mu d, and it equal the following sum from from 0 to m -1 in power t of the binomial coefficient on m of t, and this is equal 0. Yeah. Now let alpha beta from the class set of function s, then formula two is equivalent the following that alpha is equal iota star b, and formula 3 is equivalent that beta is equal mu star a. Also by the formula 4, these two formula are equivalent, and our proposition is proved. Next proposition. The number of conjugation classes of primitive words of the land and our alphabet with k letter is equal ln of k, 1 divides n, sum from such product mu of n divided d multiply k in power d, such d which divides n. The proof. The formula is immediate corollary from the formula 1, yeah? K in power 2 is equal to the sum of such product where d divided n by Möbius inverse theorem. So, very nice notion for the word of our alphabet. A non-empty word of our alphabet, a capital, is called unbordered if no proper or non-empty prefix of w is not a suffix of w. So this means the following. So if we have word via and w, then if we consider any representation this word as a, x, b, where x may be empty word, then w is not equal, then we have that a is not equal b for any representation a and b. In other words, if the word w is an unbordered, if and only if w belongs u a capital plus intersection with u a capital plus u, this condition implies that u is equal 1. If the word w is bordered, that w a capital star intersection a capital star w is equal w a capital star w union with the word w. And the following interesting proposition: let a be an alphabet with at least 2 letters. any words, for any non-empty words, from this alphabets there exist a word from Формальні our alphabet a capital, such that the word UV is unbordered. We shall prove this sentence. So let A be the first letter of the word U, and we put B be any letter from alphabet A capital which is distinct from the letter A. Let us verify that word W, which is equal to U, A, B in the power the length of the word U is unbordered. A non-empty prefix T of W start with the letter A here. It cannot be a suffix of the word W unless the T is greater, the length of T is greater the length of the word U. But then we have that T is equal as A B in power of the length U for some word as from our alphabet A capital, and also we get that T is equal U A B in power of the length of the word S. Therefore, we get that the length of the word S is equal to the length of the word U, and hence we get that T is equal W. This completes the proof of our proposition. Next, we define the two very important notion of the algebra, of the application of algebra in formal language on the theory of algebraic codes and the theory of algebraic automaton. Let A capital be any non-empty alphabet. Then the free group, which is denoted A capital in the power or with dots on alphabet A capital, is defined in the following way. Let A capital our line be an alphabet in projection with A and disjoint from A capital. Yeah, we denote by A maps to A our line the projection from the alphabet A capital to the alphabet A capital our line. This notation is extended by setting for all letters from the union of these two alphabets, and also we put our line is equal A for any letter from this alphabet. Let delta be a symmetric relation defined for the word U and V our this alphabet, and any word from any letter from this alphabet, we put that U A our line V is equivalent to U V up to model delta. So what does this mean? The idea of this is the following, that the word of such form U, so the word where A is the letter from this union, so such word is equivalent UV, yeah? And hence our line is equivalent to empty word. Yeah. So we put that the row is a reflexive and transitive closure of this symmetric relation. So what is the reflexive and transitive closure of any relation? Very simple. Just a moment. if we have lambda any relation over set x, the transitive closure of the relation lambda is delta x, where delta x is the diagonal of x, yeah, is equal. So that are pairs or the parts where x is, belongs x capital. The union lambda in power 2, the union and so on, the union lambda in power n, the union and so on, where lambda in power 2, lambda in power n is a composition, composition of lambda, yeah, and lambda in power n, the sequence of and composition of lambda, yeah. This relation is called the transitive and reflexive closure of the relation lambda on the set x. Next, then the relation rho is a congruence on the semigroup. So in this free monoid, our alphabet A capital is the union of A capital with our line. So what is a congruence? If we have monoid or semigroup M, we can consider the equivalence relation on M, and if this equivalence relation has the following properties, that if ST belongs lambda, then AS and B A T B belongs lambda as well for all AB from the monoid M. In this case, the equivalence lambda on the monoid M is called a congruence. Similar, I get the definition ours as semigroup S. Then we consider the quotient monoid by this congruence rho, and the quotient monoid is a group. Indeed, for all elements from this alphabet, we have that A our line is equivalent up to the empty word this alphabet up to model the relation rho. Therefore, the image of the generators of this group are invertible in the free group over or on alphabet A. This shows that all elements in free group are invertible, and hence it's a group. Next definition will be free commutative monoid or free commutative group. Yeah, if we have a non-empty alphabet, the free commutative monoid A capital in the power R or plus on or over alphabet A capital is the quotient of the free monoid our alphabet A capital by the congruence generated the pairs AB is equivalent BA for all AB from the alphabet A. And if we have the alphabet A is finite, and it consists of the following letter A1, so on, AK, then the monoid, then free commutative monoid A capital in power or plus can be identified with the additive monoid n in power k through the map be any point of the free monoid. Put the following ordered trip, yeah. We denote by alpha of delta of W the commutative image of the word W from the free monoid over the alphabet A capital, and this element of the free commutative monoid, and this map is defined in the following way, yeah. There are no problem to show that A is a monoid morphism, alpha is a monoid morphism from free monoid. Our alphabet capital onto free commutative monoid over this alphabet. I propose you to this moment. I propose you to prove these statements as exercise 3, yeah, and as exercise 2 to show that every element of free commutative monoid over any alphabet A can be expressed in the following way, where I are element of the alphabet A capital, and 1 and 2 and so on and k are any non-negative integer. So good. You have the next homework, and I finish my lecture. Goodbye.